Welcome back to our channel ClassFly community. So today we will be dealing with the lecture 6, that is the beam. That means today we will be doing the topic that is the bending moment of a beam and expression of beam. So let's move on and see. So first of all is the bending moment of a beam. So the first thing which comes to your mind is, what is a beam? So a beam is a structural member whose length is very large compared to other dimensions. So think whatever the other dimensions means, whatever the thickness or whatever any other dimensions it is, but the main important fact is that the length is very large compared to other dimensions, any other dimensions. Now, in the simple theory of bending of beam, the shear stress are neglected and only tensile or compressive stresses are considered. So, if you don't know the shear stress and the tensile or compressive stress, you can watch the previous lectures and then you can understand this particular words or particular term. Okay, so you need to know that in bending of beam, the shear stress will be neglected and only the tensile or compressive stress are considered. Compressive stresses, from the word you can understand that it will be compressed, whereas the shear stress means that it will displace. So you will get the idea by seeing the previous lectures. Now what it says that consider a beam fixed at one end. So this is the beam which is fixed at one end and the other will be loaded with a weight. Due to the applied force, a force of reaction is set up at the fixed end. So here there will be a force of reaction which will get set up. These two equal and opposite forces constitute a couple which tends to rotate the beam. So what happens due to this equal and opposite force, what happens? The beam starts rotating. Since the beam is elastic, a restoring couple is set up to bring the beam back to equilibrium. That means as the beam is elastic, that means elastic means what? That means it is whatever you do, whatever the force you applied, deforming force you applied, it will come after the deforming force ends, it come back to its original shape. So due to that, here also beam come back to its equilibrium position. Now let's move on and see what happens. The beam can be imagined as made up of a number of longitudinal filaments. That means the beam whichever is there, it is made up of many, that means numerous number of longitudinal filaments. Under the applied load, the upper filament will undergo extension and assume a convex form, and the lower filament will undergo compression and assume a concave form. So this is the upper one and this is the lower filament. So one will assume a convex form and another will assume a concave form. Now the filament that does not undergo any change in the dimension is the neural axis. So a neural axis you will see just now after this, that one will be your, that means that filament which does not go any change will be the neural axis. We will go through this portion again. Okay. Now the magnitude of extension, compression will depend on the distance of the filament from the neural axis. So whenever you will see that the magnitude of the extension will be the distance from the neural axis. That means that whatever the compression will be depend on the distance of the filament is from the, whatever the distance will be from the neural axis, that way the magnitude of the extension will depend. The moment of the restoring force is called as bending moment of a beam. So as I told, we will go through what is the neural axis, all that. See. So this EF is a neural axis and this is the upper filament and this is the lower filament, right? So see, let ABCD be a section of a beam. So this is a ABCD is the section of a beam. EF is the neural axis. As I told, this E and F is the neural axis. Under the action of the external couple, the section will bend into an arc without any change in the length. That means there will be no change in the length of the neural axis, but it will have a bend. The upper filament will undergo extension and A-B is greater than AB. That means this one, that is A-B, is greater than this AB. So this is the upper filament and this E-B, that means the change which happened will be greater than the original. But the lower filament will be subject to compressive stresses. So what happens here? C-D' is less than this CD. That means the change in the lower filament will be less than the original one. The beam is bent into an arc of a circle of radius. So this is the radius, which is R, and its center is O. So consider a small portion of the neural axis. So we will consider a small portion of neural axis, that is EF, subtending an angle at the center. So this is the angle which is being formed. So A-B' is another small portion of the filament, A-B' which is at a distance Z from the neural axis. So this is the another one which is get formed, which is at a Z distance from the EF, which we have assumed as the small portion. So let's move on and see that. So in the absence of bending, A-B' is equal to EF. That means when there will be no bending, at that point of time, this A-B' will be equal to this EF, which will be equal to the radius and the angle theta. And A-B' is equal to R plus Z bracket theta. That means R and Z means this distance, which and the theta. Strain in the filament is A-B' is equal to this one minus this one divided by R theta. So see, when we multiply this, R theta gets cut and we are left over with Z by R. That means distance by the radius. So if delta A is the area of filament of A-B', which is at a distance of Z from the neural axis, then Y, which is the modulus, will be equal to delta F by delta A by Z by R. Okay, so delta F is the force acting on the filament. So force acting on the filament will be what? What happened? See, Y, Z. So see, delta F by delta A into Z, and this R will go up, right? So Y and Z and delta A will be this, and R will be divided. Okay, so there will be a divide sign here. So the divide sign got missed. Sorry for that. There will be a divide sign here. And the moment of force about this neural axis will be equal to Y Z dot Z. The bending moment of the beam is obtained by summing over the moments of all the filaments above and below the neural axis. So what we will do? We will do a summation. And how we will do? We are doing summation of Y by R delta A Z square. Okay, so see, Y by R is constant, so it will come out. So, and the summation is delta A Z square. So, Y of Ig by R it will become. So, Y is the Young's modulus, I is the radius, and Ig will be the bending moment. Okay, so Ig is equal to summation of delta A z square, which is equal to AK square, and it is the geometrical moment of inertia and which depends on the area of cross section A of the beam and the radius of gyration, that is K of the area about the neural axis. So it is the geometrical moment of inertia depends on the area of cross section and the radius of gyration, that is K of the area of the neural axis. Now when we move on, we see that for rectangular cross section, Ig is equal to BDQ by 12. So B is the breadth and D is the thickness of the beam. And for a circular cross section, it is pi r to the power 4 by 4, where r is the radius. So I hope all of you understood how we will determine the expression for bending moment of a beam and what is this bending moment of a beam. So today's lecture ends here, and if you have any queries you can comment us down below, and till then be happy and have a great day. We will surely look after your queries and contact you. And again, thank you for watching.
Wow, that's impressive! You have completed a magic today. For more videos, subscribe. Join our Facebook group and Instagram page for group discussion and live magazine videos for exam preparation in an hour. We start at ClassFly community for students to learn from a friend in a simple way and support them in their own languages. If you are willing to be that one friend who saves us at the exam night preparation, then please join us by visiting classfly.in.